right, I'll begin. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you be with us today. Help us to, again, Lord, just glorify you in what we do, and just give me clarity of thought to just finish communicating this idea of Galois extension. Lord, in your name I pray. Amen. All right, so I have said some things from the Galois correspondence PDF, which I think is a nice supplement to like sections 14.1 and probably 14.2 to some extent, Dumb and Foot. On page 9 of the PDF, he comes to sort of a summary of about 5 pages of work, none of which I will actually go over in here, but it would be good for you to read it and to appreciate his examples and the development of the ideas. But ultimately, the punchline is this. Let's see here. Still about to copy down the wrong punchline. Good job, idiot. Me, not you. Let's see here. I meant on page 12. Comes to a nice, in his section 4 on Galois extensions, his theorem 4.1 just kind of gathers together all these ideas into a sort of, the following are equivalent for a finite extension. And we will be looking at finite extension, guys. I mean, there are ideas about Galois theory for infinite extensions. I mean, Galois theory is a beautiful and important chapter in mathematics, and it has been generalized in it's been done. Okay, I mean, I think the Bourbaki, for example, they pushed the limit on the way to look at the Galois extensions considerably in that chapter in math history here. For a finite extension, L over K, but we'll just need this kind of pedestrian stuff in here. For a finite extension, L over K, the following are equivalent. All right, so here it is. Number A, the number of K fixing automorphisms of L, or L over K, is equal to the degree of the extension of L over K. Number B, the fixed field of the automorphism group of L over K is what? Oh, here's these little. Did you guys write something on the board this morning? Where are these from? Weird. They're like, what that's from? This room is the holodeck. Wow. 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 This room is the holodeck. That is I think that joke may have a small audience these days. Let's see here, but I like it. Let's see. So L is just K again. So we saw a counterexample of this, right? Last time we looked at Q adjoin the cube root of 2, and we saw that the Q adjoin root, the field fixing automorphisms of Q adjoin root 3 of 2, Q adjoin the third root of 2 over Q, there's just one automorphism, right? So it's not, what's the word? That's right. All right, yeah. C, sorry, I'm trying to get somewhere today. L over K is separable and normal. What's normal mean? D, I mean, I know what separable means, that every, let's see here, what's that mean? That means every, does that mean that L is the extension with respect to a, what does separable mean for the field extension? What's normal mean for the field extension? I've lost my words here. Maybe you guys can tell me. L is the splitting field. L is the splitting field over K. All right. of a separable polynomial.
The field K is said to be separable or separately algebraic over F if every element of K is a root of a separable polynomial.
All right, let me just write that down. So this means, wait, every alpha in K, is that right? Alpha and L?
It gives an equivalent definition that's sort of...
But every alpha and L is the root of a separable polynomial?
Yes, a separable polynomial over K.
And what's the sort of equivalent way of looking at that?
Equivalently, the mutable polynomial over F of every element of K is separable.
All of a sudden I'm using F and also using K. It's my bad. I should just put K here to fix it. We're mixing sources, right? You're looking at Dummett and Foote. I'm quoting something from the Galois correspondence by Conrad. What was normal? What did normality of the extension mean? If a polynomial over K has what? Ah, okay. So in other words, you can't have the situation where you've got, for example, an extension which is not normal would exactly be that Q would join the cube root of 2 thing, because it has the cube root of 2 in the extension, right? But it's missing the Q adjoin root 2 times the third root unity, or the conjugate third root unity times root 2, right? Those two roots are missing. So it doesn't split in that extension. When we say split, we mean split completely. I could understand a person using split in sort of a more intuitive sense of it just peels off a linear factor. That's not what's meant in this language, right? I don't know what the word is for that. I guess you obtain a linear factor, I don't know, some better term for that or something. Anyway, the following are equivalent. Okay, so that's the ultimate sort of result at this stage in the Galois correspondence. But at this point, I'm going to flip back to Dummett and Foote and give a definition. Eventually. So definition. Let K over F be a finite extension. All right. Then K is said to be Galois over F, and K over F is a Galois extension. If, and so what he picks for the definition is the order of the F fixing automorphisms of K is equal to the index. Well, it's equal to the degree of the extension, I should say, of K over F. Right? And then he says we have, well, furthermore, in this case, what K over F is also called what? Right, equals to gal K over F. There is, if you look at different sources, there is some quibbling over terms here. Like sometimes people will let the notation gal k over f extend to things that aren't actually Galois groups, or something like that.
Yeah, that's what I would assume, considering that, like, if otherwise they're just equal, then.
Right? They are. Well, they are. To emphasize what it is the point of introducing the notation. Yeah. As he says here, the Galois group of an extension k over f is sometimes defined to be the group of automorphisms k over f for all k over f. We have chosen the definition above so that the notation gal k over f will emphasize that the extension k over f has the maximal number of automorphisms. All right. Corollary 6. If k is a splitting field over f of a separable polynomial f of x, then k over f is Galois. So that's over here, right? Yeah.
Is the number sign notation and the
Oh, yeah. This is.
cardinal
Yeah.
the same thing?
Indeed. So, in Dummett and footnote notation, that's this, right? Yeah. So yeah, these. So what this really is, the following are equivalent characterizations of what? Yep. Characterizations of Galois extensions. Yeah. All right. Let us move along. I'll look, let's see here. So, example 1, he looks at Q, adjoin the square root of 2 over Q, right? This is Galois, right? Is what? It's the splitting field of what? I guess, yeah, okay, and x squared minus 2. Is x squared minus 2 a separable polynomial? Well, is it a polynomial with rational coefficients? Because if it is, if it's irreducible, it's separable. And that is irreducible by Eisenstein or other arguments. But so it is, in fact, the splitting field of a separable polynomial, and consequently it's Galois. But we can do more than that, right? I mean, name calling is great, but we can do more. Basically, if we're looking for a Q fixing automorphism of Q adjoin root 2 to Q adjoin root 2, what do we got to do? We have to define, well, let me use tau again in his kind of variable way for a second. So to define tau, what do we need? We need to say what tau does to root 2, right? And your choices are pretty much plus or minus root 2. Anything else gets you into trouble. I mean, we have to send root 2 to root 2, or it's negative. So which is to say, of course, that either we get tau equals to the identity, or we get tau equals to sigma, where sigma of root 2 is equal to minus root 2, right? And it's easy enough to see that sigma squared is what? It's the identity, right? So what's the Galois group here? Yeah, 1 sigma. Or, yeah, let's call this 1. I like that. Thank you. Better. Not especially exciting, but there it is. And in fact, example 2, I'll just say in words what example 2 says. Basically says any quadratic extension is Galois. Right? Assuming that the field is not characteristic to. So, in particular, if we're looking at, K is basically equal to F adjoin square root of D, right? Either square root D is already in F, which is stupid. So it's just the trivial extension, not really an extension, right? K is equal to F. Or this example one generalizes. The automorphisms of this extension, this quadratic extension, are the identity and also the thing that maps root D to minus root D. All right?
For characteristic 2, negative square root of something is equal to its square root, so that
Exactly.
Galois group is the
Yeah, thank you. That's a good comment. So if we have square root of D equal to minus the square root of D, then just get one automorphism, right? Yeah, good point. All right, so example 4. We can look at the extension Q adjoin square root of 2, square root of 3, right, over Q. It is the splitting field of what? How about x squared minus 2 times x squared minus 3? Now, it seems to me that's not a, was that a separable polynomial? Yeah. Yeah, it is. Right, there's no repeated roots there. So if we believe the theorem that I haven't proved, this should be Galois, right? Furthermore, it should be completely determined, the automorphism should be completely determined by their action on the generators. So let's just sort through that and see how that works out. So let's see here. I'm trying to follow his notation. Well, he introduces sigma and tau as specific maps here, all right? So his sigma, what's it do? So we got to say what happens to root 2, we got to say what happens to root 3. And then we got to say what happens for tau. What's tau do? Tau does something to root 2, it does something to root 3. Both sigma and tau fix the rational numbers because that's the fixed base field. We're looking for rational fixing automorphisms. Of course, it's the prime subfield, so it's unavoidable anyway in this case, right? Eventually, at some point in our life, we'll come up with an example where we're not just working over the prime subfield, but that we're not quite there yet, you know? So sigma does what? Sigma, according to him, it maps root 2 to minus root 2. Right, it fixes root 3.
And then tau is the opposite.
Exactly.
And then you get sigma tau is the last one.
Let's see here. Yeah, what would sigma tau do?
It would switch both to the negatives.
Okay. And also the identity. So what would happen? It's fairly clear that you could calculate sigma squared would be 1, right? It's fairly clear you could calculate tau squared would be 1. It's not hard to see that sigma tau squared would be 1. Indeed, this is K4. This is the Klein 4 group. I guess, what else do we need, though, to get that? We also need that, like, sigma tau. We need that these commute, right? I guess it's impossible for it. If it's a group, it's a group. It's got 4 things in it, right? So it has to be the Klein 4 group. It's got 3 elements of order 2. But I mean, in the abstract, we should prove that there's more structure, right? I mean, you're using some group theory there, I think. Yes, indeed, by theorem of the classification of groups of order 4. Now, how do I know that this group has at most order 4?
Because the degree is square root of 2 over Q is
So I think what you're telling me is this: Q adjoin square root of 2, adjoin square root of 3, right? So the degree of this, I don't know why I wrote them in the other order, sorry, is actually equal to the extension formula, right? So that's Q adjoin root 2 adjoin root 3 over Q adjoin root 2, Q adjoin root 2, Q, which of course is 2, and this is 2, and that has to be equal. I mean, I'm kind of burying the lead here. You're right. By what we talked about last class, it has to be less than or equal to 4. But by the theorem I haven't proved today, since this is a Galois extension, it has to be equal to 4. Yeah. So once we exhibit 4 automorphisms, those have to be those 4 automorphisms we're looking for. Since it's already clear it's a splitting field, right? That's not up for grabs. So once we know it's a splitting field over Q for a separable polynomial, it's Galois. We know that there's going to be 4. There have to be these 4 Q fixing automorphisms of that extension. Sigma, tau, and the identity are those. And yes, the Galois group of Q adjoin square root of 2 square root of 3 over Q is, as you said, K4, also known as, up to, well, it's 1 sigma tau, which of course is isomorphic to Z2 cross Z2, right? If you're nostalgic for that. So there you go. All right. Now he makes a table here, which is to not cover this table when you do this example would be a shame, because it gets us to the point of the next section, which hopefully I'll get into here very shortly. So if you look at it, we have subgroup. We can look at the subgroup, and we can look at the fixed field of the subgroups, right? So what are the subgroups? I mean, finally, we've got something big enough to have subgroups, right? Go looking for subgroups of Z2 over there. It's not especially exciting, right? Finally, we have a Galois group, which is not just stupid. So there's actually subgroups to look for. What are the subgroups? Well, I'll look for the stupid one to start with. And then, of course, you've got your various copies of Z2. You got 1 sigma, right? You got 1 tau. You got your 1 sigma tau, right? And then you got the whole deal, right? So, you get your 3 proper subgroups and your trivial subgroup, the whole deal, right? Well, now, what's the fixed field of each one of these? So, I think we use the notation H, right, for subgroup. And what was our fixed field? Would be what? What was our notation for that? Would it be, I guess in our current clumsy notation, it would be Q adjoin square root of 2, square root of 3, H. That fixed subfield of that extension. So you guys tell me, what's the fixed subfield of 1? This is dumb. I mean, let me give this stupid thing a name. How about K? Right? So the whole thing is the fixed subfield of 1.
Or is K just Q join square root of 2 square root of 3? Because otherwise you would just write K.
Oh, yeah. I'm sorry. This is KH. I mean that the extension's K, right? I'm trying to use K in the same sense I used it in the definition is all, right? So, K. Okay? Sorry. I'm an idiot. What's fixed? What subfield is fixed by the subgroup 1 sigma? I mean, you look up here at the definitions. What's fixed by sigma? Right, Q adjoin root 3. What's fixed by tau? Q adjoin root 2, right? What's fixed by the whole thing? Just Q, right? I think. Yeah, this is an example of the theorem we've already stated. Yeah. What's the one remaining one that I haven't filled the gap in though? What's the field which is fixed by 1 and sigma tau? It's Q adjoin root 6. Very good. So, if you look at this, we can draw a picture, right? On the one hand, we have 1, right? And then subgroups, subgroups 1 sigma, 1 tau, 1 sigma tau, right? Indeed, it is upside down. Down here is my K4, since I'm tired of writing it. And then correspondingly, I've got K, right? I've got, let's see here, what's the, yeah, Q adjoin root 3 is Q adjoin square root of 2, I suppose, Q adjoin square root of 6, and then Q. But yes, the inclusion is reversing, right? That's the thing, like we started talking about in that previous class. The correspondence between subgroups and fixed subfields is inclusion reversing. Example 5 in Dummett and Foote is lengthy, all right? So I'll skip that one for now. I'll mention example 6 because it has an important feature. Example 6, he looks at Q adjoin the 4th root of 2, right? And he says that this is not Galois over Q since any automorphism is determined by where it sends the 4th root of 2, right? It's fixed by its action on the 4th root of 2, all right? And what are the 4 possibilities? What are the 4th roots of 2? They are plus or minus the 4th root of 2, of course, right? And then plus or minus I times the 4th root of 2, right? Let's see here. We're basically just saying x to the 4th minus 2. If you factor it, what happens? So that's x squared minus 2 times x squared plus 2, right? Which is x minus root 2, x plus root 2, x plus I root 2, x minus I root 2. This we can do without even if you don't know complex analysis, you can factor this thing, right? And the point is, the splitting field is not that, right? Because that's not a complex field. We're missing the plus or minus I roots. So that's not a splitting field. Consequently, this is not a Galois extension, right? But here's the interesting thing. If you look at, maybe I should write over here, if we put the field Q adjoin the fourth root of 2, well, that's an extension over Q adjoin the square root of 2, right? I mean, is the square root of 2 in the Q, I mean, excuse me, is the fourth root of 2 in Q adjoin root 2? No, right? So this is, in fact, an extension, and that's, of course, over Q. So what's the, trying to remember here.
Your factorization is wrong.
Oh, no.
You should have square roots of 2 dash second line. And then fourth roots of 2 in the third line.
Oh, yes, yes, yes. Thank you. Most appreciated there. Now the hangnail in your mind has been clipped. It's good. So the point is that you can prove, of course, that this, we can look at this tower of fields, if you will, Q adjoin the root 2, then adjoin the fourth root of 2, right? We know by my arguments over here that it's not Galois, right? I mean, you can see it right here. It's not the splitting field. Or you could work through the mechanics of how the automorphism has to send fourth roots to fourth roots, and that's just not, you don't get enough automorphisms to meet, condition A here. However you want to look at it, right? You got choices in terms of how we look at it now. And, for applied problems, we should use whichever choice is most convenient to us, right? But this is a degree 2 extension. This we know. Altogether, this is a degree 4 extension, right? So this is also a degree 2 extension by just dimension counting, if nothing else. So each extension here in the chain is Galois, because it's a quadratic extension. So what we're looking at is a Galois extension of a Galois extension, which is not Galois. So that's one of the things you might be tempted to think is that the Galois extension of a Galois extension is Galois, but it's not the case necessarily. Right, so that's one thing. Now there is a very greedy example here, which we should write down because it's just beautiful. And I think we can get away with, we won't need this again, I don't believe. There's lots more about the mechanics of how this fails in both in earlier in Dummett and Foote and also I think in Conrad's, Professor Conrad's Galois extension PDF. Lots and lots of details in there. All right, so this is example 7. And here we are looking at the finite field p to the n over the finite field characteristic p. So here p prime, obviously, right? And he says, okay, well, this is a Galois extension because we have, remember we proved this, x to the p to the n, right? X to the p to the n minus x is separable, right? You differentiate this thing in a field of characteristic p, you get -1. It's got no zeros, so of course there are no common zeros to this polynomial. So it's separable, which means that it's not only is it separable, we've also argued before that this is a this is the splitting field for that extension as well. Right. Let me put it correctly. This extension is the splitting field of this guy, right? So what's that mean? He says, thus, the group of automorphisms for this extension is of order n. This is order n, right? Is that right? Wait a minute. Huh. It's a splitting field over fp for the separable polynomial x to the p to the n minus x. It seems like that has degree p to the n. How is it that the group of automorphisms for this extension should just be order n?
Problem 10, section 13.6, we can raise something to the p's power, and then we denote that map by p, that's the Frobenius map, and then we can apply that operation n times, and then we get back to the identity. But if we do something that's not a power of p, then we're not going to have an automorphism because the binomial expansion doesn't work out.
Right. Yeah, I'm just struggling to remember the yn. Is that just, I'm not just...
I can pull up my proof.
No, I mean, maybe it's just I'm not paying enough attention to the base field being fp. That's what I was... Right. So it's not, I mean, obviously it's not that. So can you explain to me why?
No, I don't know why.
Oh, okay.
Just asking if that was what you were
That is what I'm puzzling over because, of course, over here, this is a degree 4 polynomial. We have a degree 4 extension over Q, right? And I'm telling, over here, I'm claiming we have a degree p to the n polynomial. And I mean, he said that he says here the number, the group of automorphisms for this extension is order n. But I know from the equivalence theorem that the number of automorphisms is the degree of the extension.
Right.
So
What is that going to be?
Well, if you have a degree and then the cardinality of FDN will be a B2N. So
see, I think this is the thing is I'm ignoring the distinction in the base fields, right? This is over FP. Oh, yeah, I'm an idiot. Well, it's not, I mean,
P to the N, not P to the N divided by P. I mean, the dimension of FPN.
there's something dumb here I'm forgetting. What you just said was,
I mean, if you have a degree N with a base field of P element, then the vector space will have P to the N elements.
Yeah. Are you asking about why the polynomial is in degree n?
I mean, I think that polynomial is degree p to the n, right?
Yeah.
Yeah.
So is your question why isn't the polynomial degree n since the extension is degree n?
Why is the extension degree N?
Yeah, that's my question is really why is the extension degree n?
So the polynomial must not be irreducible, right?
The polynomial must not be irreducible. Right. That must, right. That seems inescapable, doesn't it? So the Frobenius automorphism, as you were telling me a second ago, Sam, is this thing, right? The p power. We know that that's an injective homomorphism, and it's surjective since Fpn is finite, hence an isomorphism. This automorphism of Fpn gives the Frobenius automorphism, which we shall denote by sigma p. Iterating sigma p, we have sigma. Well, maybe I should just keep working instead of trying to. Maybe I'm trying to see the end of the example at the start, huh? Let's see. Here's so sigma. Sometimes they'll say something like the extension is degree n. It follows the group of automorphisms for this extension is of order n. He doesn't say by this theorem or by our previous discussion, and then there's like a paragraph, right? So maybe this paragraph is actually what proves that it has degree n, right? And we should just keep going rather than trying to put the horse before the cart or whatever. Oh, wait a minute. Yeah. Let's see here. Undo that. So if we take sigma p squared of alpha, what's that equal to?
Alpha squared.
Because that's going to be half to the p to the p.
Right. Alpha to the p, also known as alpha to the what? P squared, yeah. And so I think if we continue this, if we have sigma sub p to the j, and alpha, we get alpha to the p to the j, right? Until we get to what? Until we get to n minus 1. When we get to n, what happens? Sigma p to the n is alpha to the p to the n, right? Which is 1, I think.
No, it's alpha.
Oh, it's alpha again? Oh, right. So you see what we have is we have the situation that sigma p to the j times sigma p to the k is equal to sigma p, well, sigma p to the j plus k, right? Mod what?
Mod n.
Right. Which means that there's a natural isomorphism to the cyclic group of order n here. He says no lower power of sigma p can be the identity, since that would imply that alpha p to the I is equal to alpha for all alpha in F, the finite field of order p to the n. But that's impossible, since there are only p to the I roots of this equation.
Yeah.
It follows that sigma p is of order n in the Galois group. So this is a particular automorphism, right? This is the Frobenius automorphism. Basically, this calculation I'm sketching shows that this automorphism has order n, right? Which means it's going to generate a subgroup of order n inside the Galois group, right? And then what? And he says, which means that the Galois group is cyclic order n with the Frobenius automorphism sigma p as the generator. So he is claiming somehow that he knows that this extension has degree n independent of this stuff, actually. So he knows that this has degree n, and then the observation that this is a cyclic element of order n means it's the generator for the Galois group. So again, I come back to the question, how do we know that this, now this is exactly, the part I have not. How do we know that is the case? This is obvious?
It's just by cardinality alpha.
By cardinality?
Yeah.
Oh. Thank you. So yes, by counting, my old nemesis. It's okay. Why should I need to know how to count? What's my job? Let's see here. All right, so that brings us, finally, to section 14.2. Now, what's the deal with 14.2? What's that about? Just to give you a quick preview. If I could find my, put it over there. So, of course, that's the section 14.2 in Dummett and Foote is on the what? The fundamental theorem of Galois theory, right? Which basically, we look at more of these field diagrams and the corresponding fixed field subgroup of the automorphism diagrams, study the correspondence between the lattice of fixed subfields versus the lattice of subgroups of the Galois group, and understand the interplay between these two. There's a really, really neat interplay which both shed light on each other, and that's what we're after in the next section. The actual statement of the theorem is pretty lengthy, but if you understand examples, that's really more where we're going to be operating at. So anyway, sorry I have not proved everything, but I think it's better for everyone involved to spend most of our time and energy on examples in here. I do think you guys will read the proofs, especially as the examples settle in. Then reading the proofs will make more sense to you. If you guys were graduate students, not undergraduate students, I would say you should have already worked out the proof for yourself, and how dare you get out of my class or whatever. But you have other things, important things to do, like go to convocations with important social dignitaries and intellectual, titans of our time, right? Relationship experts, as it were. So.